Good afternoon. So let's look at another property that is important for materials, or it's important to actually analyze the structure of materials, and it's called as the radial distribution function or the pair correlation function. So it essentially is a reflection of the underlying order that's there in the material. For example, if you have a solid, it has long range order, and if you have liquids, it has uh, short range order only. Okay, so we will actually take a look at what this exactly means and how it is actually calculated using LAMMPS. So this is demonstrated so as to show how you can actually calculate properties in LAMMPS which are not per atom but for the entire system. Okay, this is for the entire system, right? So if you consider a solid, okay, all the atoms are arranged in a periodic manner, right? So if you sit on any atom and start going away from that atom, for some distance you are not going to find any atoms, any new atoms, right? But suddenly at a particular point at a specific distance, you will start seeing a certain number of atoms, right? That's basically the first nearest neighbor to that atom. Then if you continue going further apart from that, again you will not see any atom until you reach a next distance, right? In that manner, if you keep going farther and farther, you will start seeing atoms at specific distances only. So if something like that happens, then it basically characterizes a solid. So something like this. So this is basically telling you that the probability of finding an atom at this distance from a given atom. So say you're sitting at 0, the coordinate is 0, and as you start going away from the center of that atom, all of a sudden at this particular distance you will see a large number of atoms. Then again you see no atoms, you see a certain number of atoms, and this continues. If you see a radial distribution function that looks like this, it is basically a solid. Okay, and for liquid it is going to look something like this, and for gas it's going to look something like this. Okay. So what is the radial distribution function and how it is defined? So the radial distribution function or the pair correlation function, G of R as we will call it, is basically the ratio of the density of atoms at a given distance R from an atom divided by the average density of the sample. So basically number density, number of atoms per unit volume. So how this is calculated is, you sit on a particular atom and draw a spherical shell, say of thickness dr, okay, at a distance r, okay, and then you basically compute the total number of atoms that are there in that spherical shell, divide by the volume of that spherical shell. That would be the density, number density of atoms in that spherical shell, and then divided by n over v, which is basically the number density of the entire simulation box that you're looking at. So you sit on an atom, this is actually the spherical shell. So if you look at this spherical shell, you can count how many atoms are basically present. So 1, 2, 3, 4 in this case, and then you can divide that by the volume of this shell, and then you can divide that entire quantity by the density of the atom. So this is the expression for G of R that is generally used in molecular dynamics to actually calculate the radial distribution function. So n is basically the number of atoms in the spherical shell, okay, of width delta r, and omega is basically the volume of the spherical shell. So n over omega will be the density at this r, and that is being divided by the average density of the system, and that kind of gives you a measure of what is the probability of finding an atom from a given distance, in a given distance from the atom that you are sitting. Okay, now you want to not do this just for one atom in your entire sample. What you want to do is, you want to do this for every atom for some distances, and do this for all the atoms and average it. Average it over all the atoms and average it over time as well, because all these things could be changing with time since the atoms are oscillating about their mean positions, right? So there are two averages. One is you do this for every single atom and then average that over time. Is that clear? So this quantity g of r is going to be a vectorial quantity where for every distance r you have a particular value of g of r. Okay. So that is the reason why it looks why it has this form where you have a large, where you have a peak at a specific distance r. So this is called the radial distribution function, and we have to have two averages. One is over all the atoms, another one is over time. So this should be clear that this actually is for the entire system, right? So you have to use this fix called fix average per time in order to why is it a vector quantity? It's a vector quantity because what you are going to get out of this calculation is the following. You are going to get a distance r, and for that distance you are going to get the corresponding g of r. So for various distances you are going to get various g of r quantities. So what it calculates is actually a vector.
No, at different points in space it has got different values, but why should that quantity itself have direction?
It's not direction. It's not like a direction. I'm just telling you that it is not a scalar. When it is calculated, it is going to be a vectorial quantity where you have a g of r for every r. That's it. I'm not telling you that it's a vector with direction and all that. I'm saying it's a column vector. It's a column. That's why I said it is not like a pressure. It is but a column vector. Okay, that's what I meant. Okay. So first let's do this for a solid. Okay, I have taken input 9. It's called as input 9 is the input file for this. This has already been uploaded on Moodle, so you should be able to find it. Okay, so I want to first look at it for a solid. So since I'm still working with argon, I better look at extremely low temperatures in order to calculate this radial distribution function. So everything is pretty much the same until we come to this point where I'm going to say that you create velocity distributions of about 5 Kelvin. Okay, just arbitrarily I chose that. Okay, and then I'm going to be running a NVE simulation, and it is during that simulation I want to gather this data of g of r. Okay, so it is during this portion that I would be gathering the data for g of r. So this entire thing is just a NVE simulation which is going to run for about 10,000 time steps. Now over here I have the command which computes the radial distribution function. So it's again a compute. There are various different computes that we saw in the last class. I showed you a big list in the LAMMPS documentation, right? And RDF is actually the compute ID which I am going to refer to later on in the script. All is basically the group of atoms over which I want to make this computation, and this is actually this type. What is the compute style? So it's RDF, radial distribution function. 100 is basically the total number of bins between the atom that I am sitting at and the maximum radius that I want to examine from the current atom, from every atom. Okay, so basically it is, so this would be a cutoff distance, basically a radius that I am defining, and the maximum radius that I can go, and then the bins would be the total, the basically telling me how many such shells that I basically want to take when I am calculating my radial distribution function. So again, in LAMMPS, this cutoff that you give here should be equal to or less than the cutoff that you give for the potential. If you want to examine it more than that through LAMMPS, you should actually change this value right here, or there is some property called, there is some other way by which LAMMPS allows you to modify the cutoff. You should use that. But for the purposes of this class, 10 angstroms is more than sufficient to examine the radial distribution function. So we will give a cutoff of r, and then this is just computing the RDF for one state, right? We want to be able to average this quantity for over all the atoms and then average it over time. So that is basically done by this command right here, where you say fix, again this is a fix ID, all the atoms, average over time, but now it's not average per atom, it's average over time of this global quantity, okay, and this should now be clear to you. I am running for 10,000 steps, so I want to print out every 10,000 steps, which means I want to have only one average over the entire run. This is basically the number of steps that I want to choose, which is also 10,000, and 1 is basically the take input from every step that you compute the RDF, and then the compute basically prints out is actually an array. So you have C underscore RDF of 1, which will basically contain the values of the corresponding R's, okay. C RDF of 2 will basically contain the corresponding G of R's, and C underscore RDF of 3 is going to contain the corresponding integral, which is basically which is related to the coordination number of the atom at that spot. So the fix RDF, if you, so what did I use, what file name would I use? I use RDF underscore solid.txt. So VIM RDF underscore solid.txt looks like this. So it has some time average data for fix RDF, time step, number of rows. This is the time step, 10,000, that's what we want, averaged over all the 10,000 time step. Number of rows is 100, and this is basically the, it prints 4 things, it prints 4 things. The first is just a serial number, the second one is basically the corresponding value of R, the third column is the corresponding G of R for that data, and the third one is the integral of G of R. The integral of G of R, what does it give you? It gives you basically the coordination number, that point, exactly. So I'll just show that to you in the next. So this is what this code has generated. So as you can see, initially it's all, look at this third column right here, it's all 0 initially, and then it starts to raise, okay, it starts to raise to some large value 21.6997, and then again it starts to decrease to 0, and then again it raises to some value and keeps going on and on, right? So this is how the RDF of the solid looks like, and this is the plot that it basically generates, okay. So you know that the first, so what is the distance, so there is some lattice constant that we have used, I think we have used 4.58. So what is the first neighbor in the FCC? This is FCC lattice also. What is the first neighbor in the FCC lattice? A by root 2, right? So you can plug it in here and see if the first peak basically occurs approximately at that point.
First neighbor,
any atom, you sit on any atom and keep going, the first atom that you encounter will be at a distance of A by root 2, right?
yeah.
That is this number right here. So this is actually a signature of whether it is BCC or FCC, okay. You can actually calculate the lattice constant by looking at this, right? If you knew the structure is BCC, then you can actually calculate the lattice constant by looking at this diagram, right? Because this is the first neighbor is found here, second neighbor is found here, third neighbor is found here, fourth neighbor is found here, and so on, okay. And then the integral of G of R, actually it's the integral over the sphere, right? Because you're integrating, because you've always considered a sphere in this particular case. So 4 pi integral from R1 to R2 R square G of R is going to give you the total number of atoms that is present at that particular distance between R1 and R2, okay. So by changing R1 and R2, you can find the first, second, third, and so on nearest neighbors that is actually appropriate for this particular material model, for this particular material. And for FCC, the number of first nearest neighbor is 12, then is 6. The next distance you will find only 6 neighbors. After that you find actually 24 neighbors. After that you find 12 neighbors, okay. Of course we wouldn't have thought about such far off distances which is precisely the reason why you can actually use this information to get that. So this is just plotting the final column of the radial distribution function, which is the integral from 0 to 1, 0 to 2, 0 to 3, 0 to 4 is what is being plotted here. So as you can see, right at the point where you have the first nearest neighbor, you will get 12. So it is first nearest neighbor, number of first nearest neighbor for every atom is 12. The next is 18, which is basically 12 plus the 6 nearest neighbors, because this involves an integral from 0 to the second nearest neighbor distance. Okay. Then you have from 12 to 42, which is basically plus 24. So 12 plus 16 plus 24 and so on. So this will tell you this is kind of indicating to you what is the number of first nearest neighbors, second nearest neighbors present in the crystal structure. So this sort of information can be obtained by looking at the radial distribution function. Okay. And the calculation, yes.
So when you plot the 0 of R versus R, it is again averaged with all the R's also. I mean all the atoms.
All the atoms.
So how do we associate meaning to that R?
Which are?
Like where is our origin and all that?
At every atom. Sit on every atom. Sit on every atom, draw a radius of 10 angstroms, divide it into 100 bins, start looking at how many atoms are there, sum it all up, keep that in an array. Sit on another atom, do this, add them up. Sit on another atom, do this, add them up. Keep doing it over and over again until you have done with all the atoms, by keeping in mind the periodic boundary conditions, because an atom at the end is actually closer to the atom on the other end. Okay, it's not far away because it's actually located here. So keeping in mind the periodic image of every atom, you should do this for all the atoms. It can take some time to write such a code. Okay, that's why LAMMPS actually does this for you, and it's pretty useful. Yes, it sits on each atom each time.
So basically what is being done is that for each atom RDF is being calculated, then it is being averaged for the entire system
And average over time also, because if the atoms are actually,
over time.
yeah, because for this case it might not have made a huge difference because the atoms are hardly oscillating. But say you want to obtain the radial distribution function at some finite temperature like 300 Kelvin or 400 Kelvin, then the atoms are actually oscillating about their mean positions. So at every single shot, the atoms are not exactly in the FCC positions. There may be minor deviations because they are oscillating, isn't it? So if you really want to see the FCC structure, you have to average them out over time as well, so that you can in fact see that it is still a solid. The atoms are just vibrating about their mean positions.
Would that be same as calculating an average configuration and then doing the average?
Yes, yes, it should be the same. Yep.
So if we want to use this
But that would be very hard to do. Every time you have to generate. So this one has generated 10,000 different configurations. Now you are, if what you are saying is generate 10,000 different random positions for each atom and then average it out. Yeah, it's the same thing.
we want to use this formula for calculating the
This one, 4 pi.
yeah,
Yes,
for calculating NR at a distance of
between R1 and R2. Total number of atoms that you can find from a given atom between the distance R1 and R2. From R1 to R2, how many atoms are there surrounding any given atom?
okay. So there has
That-
to be a difference between upper limit and lower limit, no matter how small
Yes,
that is.
yes.
But if you want a specific distance, we can make that difference very, very
You will get 0 if there is no atom. Yeah, if there is no atom, you will get 0. Anything specific?
So, so this question was regarding change of order of integration. So
Whose question?
first you average all the space coordinates and then you calculate.
No, what he says is, instead of averaging it over time, you have different ensembles. It's just instead of saying time average, he says do ensemble average. You have different positions of each and then do the same thing, and it's the same thing. because time averaging and phase averaging are the same, or the ensemble averaging is the same. So this is how it looks for a liquid. Okay, there is one single peak showing some sort of short range order, but after that you find one small peak, and then the radial distribution function converges to 1, basically telling you that the probability of you finding an atom from, if you sit on any atom, if you go far enough, there is always a probability, the probability of finding another atom is a 1. That's what this is basically telling you. Okay, this is how it looks for a liquid, and this is something that it looks for a solid. You don't see this additional peak. So even shorter range order is found for gases. So the gas code is also here. So it's so I generated this input file for the gas slightly differently. So what I have done is I have used my previous experience on what the volume should be for 1 atmosphere and 300 Kelvin from exercise 8. I really know the volume, so from that I can actually construct the block size. Okay, and after that, see, this is there are some new commands here, so I should specify that. So this gaseous state was not done like what was done for the for exercise 8. In exercise 8 we were learning several things, so we started off from really weird configuration, and then we slowly equilibrated the system to actually be able to generate a system which was at equilibrium 1 atmosphere and 300 Kelvin, right? Now I don't want all that, I just want the gas. Okay, I want the gas. From previous experience I have figured out that my gas at 300 Kelvin and 1 atmosphere, the system volume is something, it turned out to be something, and the cube root of that volume is basically giving me my box dimensions, which is what this 549.8606 is. Okay, then what I have done, after creating that box, I have to throw in atoms inside that box at random positions, right? Because now there is no structure to this whole gas. So I want to throw 4,000 atoms. Remember the previous case also we had only 4,000 atoms, 45.8, 4.58 generated 10 by 10 by 10 unit cells, which had about 4,000 atoms. So you had, so I just say create atoms 1, random, at random positions, create 4,000 atoms. This is the corresponding random seed, and this is basically the region where I want to generate all these atoms. So it just generates all these atoms. After doing that, of course everything else is the same. I just want to calculate the volume for whatever reason. So I then, after that, I have introduced here another command. So remember previously when we minimized the system, it just minimized holding the box fixed. That means the box dimensions were fixed, right? There is also another command here where, as it is performing the minimization, you may be able to adjust the box sizes. You may not necessarily have to start off the NPT from a really far off state from what you require. Okay, so for that you have a fix called fix relax box all. Relax box is basically a fix ID. Okay, it is not a keyword of LAMMPS. This is a keyword of LAMMPS which says box/relax, isotropic, and the corresponding pressure. So this one can also adjust the size of the box really well. Okay, what it does is, as it is performing this minimization, it will perform these minor changes. So this is a new command that you can learn. Okay, then I gave a high velocity here. Okay, all these things may not be needed for this particular exercise. Basically just creating a very high temperature, a distribution of a very high temperature, and then equilibrating it for long enough, and then I do a NPT for a very for about 50,000 steps, which may not be needed. I just wanted to make sure that it equilibrated at 300 Kelvin. Okay, we saw previously that 50,000 from a really far off state was also sufficient for this case. Okay, for this since I've already given reasonably good starting configuration by using the right volume of the box and also did a fix relax box after that, this NPT may not need so much, but I've just given it here. Then I checked for equilibration and then performed compute of the RDF in exactly the same manner. And again I have performed the RDF only in the last final NV. Okay, this is a, so 20,000. This happens to be the final time step that you would reach until this point. Okay, like what we discussed yesterday, this one. Okay, so it is going to print out the data every 113912 time step. Okay, and you are going to average over 20,000 steps every steps, and the same information is actually printed. So take a look at, it looks something like this, and again it kind of converges to the value 1. Okay. So this is the way you can use LAMMPS to actually calculate your radial distribution function. Now a lot of features have come in this visualization software called Ovito, which can also calculate the radial distribution function. So yeah.
So only way to get that one from these samples is when you manually grab across this arrows.
But it's easy, no? You know how many steps you have run, so it should not be too hard to do that.
But if I
Or you can define compute. You can define a compute to calculate the total number of time steps. Calculate it.
It seems like it's some way we are hard coding.
Yes.
Now if I
Yes.
do some playing around in the beginning, then I have to.
You have to keep this in mind. You have to keep this in mind, or you can make everything a variable. Run also can be made a variable. Then you can keep that in. You can
And
add them. Say variable equal and add them, and then give that value here.
So what difference did we get if we now we are using laps? What difference are we? What is the difference? Instead of using that size, fixing the size as we were.
What is that? What is the difference you get?
When we are using relax box instead of using the previous command.
NPT.
What
Is fixed relax box has a very rough relaxation. Okay, it just approximately changes the dimensions of the box so as to make the system to get as close to the pressure that you want. It is not really a barostat. It is not something that is going to maintain the pressure over time or anything. During the process of minimizing the energy of the system, it does a little bit of adjusting the box sizes. That's it. After that, you still may have to do, mostly you have to do NPT. But if you're starting off from a really far off configuration, this can be a crude way to actually bring the system to approximately the size that you want. Did you notice when we did the previous exercise 8, when I showed it to you in Ovito, you start off from a really small box and this thing just became extremely large. Now go and try that by first using a fixed box relax, following that try to do an NPT. The minimized structure itself will be quite large, and after that the NPT will have to do only a little bit of adjustment in order to bring the box to the right, close in, make it more accurate. Okay, basically NPT is only fine tuning rather than rapidly changing stuff. These things are important because when you're working with solids, it will play a very important role.
Said the GFR is probable,
Yes,
but it's not really a probability.
is not.
It's not really a probability because
It's not really a density at R divided by the average density. So it kind of gives you the probability of,
go above 1.
yes, in that sense, yes. Yes, it's not like a, I say it's like a probability. It's a probability that you will find an atom at that distance. If you see a peak, it's a probability that you will find an atom at that distance.
More like abundance, right? With respect to
It is more like
an abundance
abundance.
or multiples of the ideal value.
Higher the peak, the more the number of atoms, or is it the higher the peak, the more the chances of
Higher the peak, the more the chances.
within that probability, but it's not exactly probability because probability should be within.
Correct. You normalize it to 1. So it's okay. It's okay if it's not exactly viewed as being a probability per se, but it should not be too hard to accept that if you look at this figure, so at this point there is a peak, so it essentially means that the chances of finding an atom there are high. Okay, that's it. So it's very clear that here there is no chance of finding any atom. So in that sense, it's kind of a measure of the probability of finding an atom at this distance from a given atom.
So in that case, for the fluid and the gas, so after time shift goes in kind of straight line. So how will you explain this?
What is that? It kind of becomes straight line. What is the meaning of this? It means that the density of the gas at any distance r and the density of the actual system is the same. So there is always some atom present at the distance. This peak here shows that there is some sort of a short range order that is being present. There are, if you at small distances, you always tend to find a little bit more atoms that's present for every atom. But as you go far away, it kind of reaches the average density of the entire system. That's what it means.
So in G of R is equal to rho of R by rho,
Huh.
the formula which we first saw, there the denominator rho represents the
N by V, number of atoms divided by the volume of the system.
number of atoms per unit volume.
Ah.
So how is LAMMPS getting that for calculation?
It knows the number of atoms because you only created the structure, so it knows the number of atoms.
And
It
we
knows
have provided the dimensions
of the volume, and it can also calculate the volume. Volume is a variable, right? It is a thermodynamic variable that it can print in the thermostyle, which means it knows the volume. In fact, for when you are using variables like volume, press, potential energy, kinetic energy, you don't even have to use a dollar sign in order to refer to it. You can just specify volume, VOL, and it will know that you are referring to the volume of the system. PRESS refers to the pressure. Okay. So now it's a good idea to actually see first. I don't know what's the name of the output file. Okay, so we can reduce the size of the particle. So you see how much it is expanding. So now I can actually calculate the pair correlation function or the G of R using right here for every time step. It's called as the coordination analysis. So you see right here, right below, it is basically plotting exactly the same thing, but it takes some time because it has to do it for every time step, and it is plotting that information here. So if you start off from the beginning, but it is not doing all this averaging and all that. So it starts from 1 and it has a large number of peaks, right? So I can give a, say, smaller cutoff radius. So it starts off with having a large number of peaks and slowly becomes something a little bit more messy and looking like a gas, right? So this is solid and then suddenly it becomes a liquid and then gas. So this is basically useful if you want to quickly see how the structure is behaving when you are running a simulation. Okay, so of course if you want to average it, there are several ways to do it. One way is to do it right from LAMMPS, and apparently now Ovito has an ability to actually write Python scripts which will allow you to average this information from Ovito itself. But we are not doing that in this course, but you can explore that. So is this RDF calculation clear? Say RDF calculation is just an example of global averaging, and our what is that called, velocity was an example of per atom averaging, right? So there are so many different kinds of computes, there are so many different kinds of things that you might want to average over time. So there will be a couple of exercises that I will give you where you will encounter something that has not been done here, but I am expecting you to use whatever I have taught to actually do that correctly. Check and show that you have actually understood it, and then perform proper averages of the system.